Hey guys, this is the first video related to the second PowerPoint of Chapter 14. At this point, you should have been through all the videos related to the first PowerPoint of Chapter 14. Then you should go through Chapter 21, and then we start this video with the second PowerPoint. Okay? So, in this section, we're going to study more of the intricacies of why reactions might be fast or slow. We're also going to look at how we can control the speed of reaction, and use that to our benefit in different processes. So, in order for reaction to happen, the first thing you have to realize is that if there are multiple reactants involved, they have to actually come in contact with each other so that when two reactant molecules come in contact, then they have the potential to react, which a reaction involves, you have to break a bond, maybe form a bond. You're reconnecting atoms in different ways. So in order for that to happen, the reactants have to come in contact with each other. So if we want to speed a reaction up, how do we do that? Well, we're going to have to increase the number of collisions. How can I increase the number of collisions between the reactant molecules? Well, number one, if I put more reactant molecules into a container, that's going to create more collisions, okay? Now, specifically what that means is if I increase the concentration of the reactant molecules. Now, if there are more than one reactant, say reactant A and reactant B, I can increase the concentration of one of them, or I can increase the concentration of both of them, and in either way, we may increase the number of collisions that can occur, okay? Again, we'll talk about that more later. We can also, beyond concentration, physical state also matters. If I mix together two solids, that solids tend to react slowly because the reactant molecules aren't really moving very much. So when you mix two solids together, the particles for the most part just sit there, and if they're not colliding with each other, we're not going to break any bonds in the reactants, which you have to break bonds to create the potential to form new bonds in its place, which is what my products are going to be. Take the reactant molecules, break them up a little bit, and then reform them in a different way. So there have to be collisions with a certain amount of energy that occur. In solid form, that doesn't happen very much. If I look at gases, gas molecules are moving fast, and when they collide with each other, there tends to be more energy involved. But the problem with gases is the molecules are so spaced out, and there's so much empty space in between them that you really don't get a whole lot of collisions going on with gases. So that's why a lot of the reactions that we study in a laboratory actually are done in aqueous solution. You can take a solid or a gas, dissolve it into a solution, and then all the molecules are within a confined space, and they're moving around so that they can bump into each other, which is how many reactions occur. Okay? So I can increase the number of collisions, but another thing I can do is I need to increase the energy of the collisions. If two molecules come in contact and just kind of bump into each other, if it doesn't actually break a bond in the reactants, a lot of times they're just going to bounce off of each other and no reaction occurs. That often would be what we call an elastic collision. We need to smash them into each other hard enough that we break a bond, which creates some unstable fragments, and then those unstable fragments will often continue the reaction, and when they reform in a different way, that'll give us the product molecules that we're looking for. Okay, so we have to have enough energy in our collisions to create a reaction. Okay, now how do I do that? Well, if I want the particles to move faster, yes, I can affect the physical state and increase it that way, but really the most common way is to raise the temperature. If we increase the temperature of the reaction, that's going to give me collisions that have more energy, and it's going to give me more collisions, because if things are moving around faster, they're also going to crash into each other more often. Okay? So temperature is probably our number one control that we can use to speed up a reaction. Now, one more little factor that can kind of come up, there are reactions where the orientation of the molecules matters. When two molecules collide, if we need to break a specific bond, or we need an atom from one molecule and an atom from another molecule, if they specifically have to crash into each other, the direction that the molecule is pointing can affect it. If they crash like this, maybe the reaction works, but if you spin a molecule around and crash in like that, then the reaction might not work, okay? So there are cases where the orientation is going to be very important. This is very common with like biological reactions that involve catalysts and things like that, where the molecules have to collide with each other just the right way in order to get a reaction to occur. Okay? So all those are factors that we need to think about. Now back to the temperature one, which is kind of the one that we focused on the most. We talked before about in order for a process to happen, we showed this graph when we were talking about evaporation or vaporization. At a given temperature, and again, the lower temperature is the blue graph, the blue curve. At a lower temperature, the distribution of energies is shifted down a little bit, and there's a very small number of particles that have enough energy to overcome whatever the minimum amount of energy is required to achieve a process. It might be vaporization, it might be the energy of a collision to break a bond. If I increase the temperature and the whole distribution shifts to the right, then the fraction of molecules that have enough energy to react or vaporize or whatever, if I can increase that number of molecules here, then that's going to speed the process up. Okay? So again, that's the Maxwell-Boltzmann distribution. We've seen that several times. Make sure you're familiar with it. Now, we say that increasing the temperature increases the rate of a reaction. Okay? So if I'm looking at a rate law, rate equals K times A is my first reactant raised to the X power times B is my second reactant raised to the Y power. So if I have a rate law, which part of this equation is going to change if the temperature changes? Okay? Well, first of all, we just said if we raise the temperature, the reaction should go faster. So I know that the rate itself is going to change. But which part of the equation on the right side is going to change with it? Because I can't increase the rate unless one of these values goes up. And the answer to that is, when I raise the temperature, it's going to increase the rate constant. Okay? The rate constant of a chemical reaction is dependent on temperature. Now I'll make one note here. The only time that K won't change with temperature is if we're doing a nuclear reaction. If you remember in chapter 21, we said that the half-life is constant and the half-life equals 0.693 over K. So that means that for a nuclear reaction, the rate constant does not change with temperature. Okay? But in a normal chemical reaction, the K value does change with temperature. That is an important separation between the two chapters. So, at higher temperatures, the reactant molecules have more kinetic energy, they move faster, they collide more often, and they collide with more energy. All of those facts are important. Therefore, K is temperature dependent. It will increase with temperature. So we can see this is a graph of the rate constant versus temperature. Well, we see this is an exponential relationship. A general rule of thumb is that the rate constant, which, again, when I look at how fast a reaction is, the easiest value for me to look at is the rate constant. The bigger K is, that would indicate a faster reaction if I'm ever going to compare one reaction to another. Okay? Now, K doubles with every 10 degree rise in temperature. So if I measure the rate of a reaction at 25 degrees Celsius, I would expect the rate at 35 degrees Celsius to be about twice as fast. Okay? It's a rule of thumb. It doesn't always work, but it's a good guideline. Now, that relationship between the rate constant and temperature, that was studied by a guy named Arrhenius. He noted that relationship, he did some calculations, and he developed what is now known as the Arrhenius Equation, where the rate constant equals A is a proportionality constant, it's called the collision frequency factor, times E, and that's the exponential E, raised to the negative EA over RT. E sub A is the activation energy of a reaction. R is the thermodynamic R value, which is 8.314 joules per mole Kelvin, and then the T has to be in Kelvin. Okay, so that's the Arrhenius equation. And what he found is that most reactions, the rate constant will follow this equation, where it's dependent upon the E sub A value, which is the activation energy for the reaction. It's dependent on the temperature, and then A, the collision frequency factor, calculates basically if there are a certain number of collisions that occur between molecules, how many of them are called effective collisions. where the molecules are colliding in the right orientation so that when they collide, a reaction can happen. Okay? So all of those values are factored in when we calculate K. Now, that's a simple equation that establishes the relationship, but we don't like to get exponential curves. We would rather convert that into a linear relationship. So how do we do that? Well, we've seen this before. If I have an exponential curve, I want to make it linear. I'm going to take the natural log of both sides. So I'm going to make a graph to get a linear relationship between rate constant and temperature. The y value of the graph is going to be the natural log of my rate constant values. The x value of the graph is going to be 1 over temperature. Okay? So we saw a relationship like this before with the Clausius-Clapeyron equation in chapter 11. This is going to be a very similar relationship where I have my y value, I have my x value, and then again, with Clausius-Clapeyron equation, we could use the slope of the graph to find the heat of vaporization for a liquid. In this case, we're going to use the slope of the line to find the activation energy. If this is my x value, 1 over t, that means negative EA over r is my slope, based on the idea y equals mx plus b. Okay? So my slope is negative EA over r, so if I multiply r over and then change the sign, then that will give me my activation energy for the reaction. The point of that is, if you measure for a given reaction, if you measure the rate constant at several temperatures, you graph this relationship, then we can actually use that data to find E sub A. So what does that look like if we're actually going to apply this ourselves? So we would perform an experiment where at several temperatures, we measure the rate constant, and then we take those, we have to do a little bit of data manipulation, where I'm going to have to convert my temperatures from Celsius to Kelvin, and then find 1 over T, so take my Kelvin, invert it to get my inverse temperatures, and then I take my K values and do the natural log. Those are the two data columns that I want to graph. This is my X data, this is my Y data for my graph. Once I do that, I get a graph, I do a linear fit, and I get the equation of the line. The slope of the line is negative EA over R, as we said before. So if I get that slope from the linear fit, then I can use that to solve for E sub A. So for this problem that we just did, here's the equation of my line. My slope is negative EA over R. So there it is, negative 19,050. So I can just set up the slope equals negative EA over R. I'm going to solve for E sub A. And when you solve for it here, it's going to come out to be probably 158,000. That would be in joules. But then if you convert it to kilojoules, you should get 158 kilojoules. That's the activation energy for the reaction that was studied with the previous data on 1 or 2 slides ago. So we have the basic Arrhenius equation. That's the one that kind of just establishes the exponential relationship between the rate constant and temperature. We also took the natural log of the K values, did 1 over T, and we set up our graphical relationship where we get a linear graph. That's nice to use outside of class, or if somebody provides the data, like on the test. If we take the data, convert it into a linear graph, and then give you the slope, you could use that information to find E sub A. That's a problem we could give you on the test. Or, kind of like the Clausius-Clapeyron equation, we could just do this calculation based on 2 data points. It's always better to have a lot of data points and establish the line. That's like the ideal scenario. But on the test, it's more likely if we're going to have you do a calculation yourself, we're going to give you the 2-point Arrhenius equation, where there are 2 temperatures and 2 K values and the activation energy. We're going to give you 4 out of those 5 values. And then you have to be able to plug it all in, solve for the value you don't know. We might be, if we give you both K's and both T's, you might have to solve for the activation energy. If we give you the activation energy, 2 of the temperatures, and 1 of the K values, you might have to solve for the other K value. or any of that kind of problem, okay? But there are 4 variables there that we could, excuse me, 5 variables. We give you 4 of them, you solve for the 5th. As an example, on this slide we have a reaction is being studied. We give you at 650 Kelvin, the rate constant is 1.66. And then at 700 Kelvin, the rate constant is 7.39. So I gave you 2 temperatures and 2 K values, and then you're asked to solve for the activation energy, which is E sub A. So at that point, you should be able to take the equation, plug everything into it. My unknown is EA. You should be able to do the algebra to solve for EA, and the answer you should get is you'll get 113,000 joules, which you can convert into 113 kilojoules. Okay? You should practice this before you come to the test. The algebra is not simple. It needs to be practiced so that you can do it quickly if needed on the test. All right, so that brings us to our next section, which is where we're going to talk about energy profiles. It's a good point to cut off the video. We'll pick that up in the next part.